In Concept A, we're going to be talking about isotopes and how to calculate their atomic mass. So by the end of this lesson, students should have a basic idea of how to distinguish between ions and isotopes. That's going to be one thing we'll focus in class tomorrow specifically about. But also be able to determine the similarities and differences between an element's isotopes and be able to calculate the atomic mass using what's called a weighted average. So just to review what we did back in Concept B, our mass number is equal to the number of protons and the number of neutrons. Remember, neutrons add mass, but they do not change the atom's identity. So if we change the number of neutrons, we'll change the mass, but not change what the element is. So in terms of subatomic particles, isotopes contain the same number of protons but a different number of neutrons. They're the same element because of the same number of protons, but they have different masses because of their different number of neutrons. So in iron 57 and iron 60, we're going to see for iron 57 a atomic number of 26, a mass number of 57, which gives us the following amounts of subatomic particles. We'll see that our protons match our atomic number and our neutrons are the mass number minus the atomic number. In an isotope of iron, iron 60, we have the same atomic number but a different mass number. And if we look at the subatomic particles, we can see they both have the same amount of protons but a different number of neutrons because of those different mass numbers. So mass number and atomic mass are not the same. Up until this point, we've talked about the mass number, and that mass number is the number of protons and neutrons. However, the atomic mass is going to be a different type of calculation. In a sample of a substance, you get different isotopes of the atom. So to report the atomic mass, we take a weighted average of all the atomic masses. That is, when calculating the atomic mass, the relative abundance of each isotope and the mass of each isotope are taken into account. So while each element has various isotopes, not all of them have the same abundance. So again, atomic mass is not the same as the mass number. The mass number is the protons plus the neutrons, and the atomic, which is always a whole number, okay, is the mass number. But the atomic mass, which is never a whole number, is the weighted average mass of an element based on its relative abundance of that element's isotopes. Alright, so let's go ahead and do a couple practice problems. One thing to keep in mind about atomic mass is that the number that you get is not the mass of an exact atom, it's an average carbon atom, in this case that I'm giving you on your screen. So keep that in mind as we go through these calculations. Also, we can look at an atomic mass to figure out what the most abundant isotope is. So for us, most of the atomic mass numbers which are found in the periodic table are pretty close to whole numbers. So we can tell what the most abundant isotope is of various elements on the periodic table. So for iron, which has 55.845, I then know that the most abundant isotope of iron has a mass number of 56. Alright, also just to note that the atomic mass comes mainly from the protons and neutrons. So since electrons are so incredibly small, ions and atoms basically have essentially the same mass. Alright, so now getting finally to those calculations using a weighted average. The first example is that the exact mass for each isotope is not given to you. You're only giving the mass numbers. So for this imaginary element, we have mass number 12, 14, 15, and 16. So how I'm going to show you is that we're going to take each of their percentages and divide them by 100 to put them in decimal form. And then I'm going to multiply each of their percentages by the mass number. So setting that up, I have the mass number times the decimal form of the percent or abundance plus the mass number times its percent abundance put into decimal form and so on. So when I solve that, I get 14.8 atomic mass units is the atomic mass or weighted average of element X. One thing to keep in mind that I always ask students to check is that their answer should be between the smallest and the greatest mass numbers or isotopic masses given to you. So 14.8 falls perfectly between those two answers, and it makes sense based on my relative abundances. Now an alternative setup, and you're going to see this in the next example, is this shown here, where I don't convert it into decimal form. I simply set it up in the percentage form, but I divide the whole answer by 100 to get 14.8 as well. So you'll see this work out in example number 2. Now in example number 2, the exact mass of each isotope is actually given to you. So chlorine 35 and chlorine 37, which are our mass numbers, we're not actually going to use because we're given the exact mass or the isotopic mass of each of them. So same idea, the isotopic mass times its percent. So 34.9689 multiplied by the 67.49, which is the percent of the chlorine 35, plus the mass times the percent, all of that divided by 100 to get a final weighted atomic mass of 35.6191 atomic mass units, which again should have fallen and did between the lowest and the greatest atomic mass. All right, so why don't you go ahead, see if you can practice this. I expect this to be in your notes to calculate the average atomic mass for an atom of silicon. All right, here you can see my work. I decided to go ahead and put each of the percentages in decimal form, multiplying them each by their exact masses, not their mass numbers, and I got my average atomic mass of 28.09, which makes sense because it falls between the smallest and the greatest atomic mass. So I know I most likely did my steps correct, my calculations correct. All right, so we will practice this a lot tomorrow, going and talking about isotopes and how they're different than concept C when we talked about ions, and also doing a lot of practice with calculating the atomic mass.